Hi, everybody. My name is Carly Benhart. I am the second year Traffic 21 Women in Transportation Fellow, and I will be introducing Corey Harper. Dr. Corey Harper is an incoming assistant professor of civil and environmental engineering at Heinz School of Public Policy at Carnegie Mellon University. His research focuses on climate-resilient transportation systems and automation in transportation. Here he uses cost-benefit analysis, modeling and simulation, and machine learning to ask questions such as, how does rain impact congestion on the transportation network? And how could robocars impact parking revenues in our central business districts? He is also the recipient of the Elsevier Atlas Best Paper Award for his work looking at the equity impacts of automation. In 2016, he was invited to become a young member on the Transportation Research Board Standing Committee for Vehicle Highway Automation. Before becoming a postdoc, he held a position at Booz Allen Hamilton in Washington, D.C., supporting clients on technical and policy issues related to cyber physical symptoms, especially helping the United States Department of Transportation with the integration of connected and automated vehicles. His presentation today will be advancing toward a smarter and more sustainable transportation system. Thank you, Corey.
Thanks a lot, Carly. Thanks for the introduction. I'm going to go ahead and get my PowerPoint set up now. I can't share my screen, Joy, so. Because I cannot share screen while other participant is sharing. All right, so as Carly said, she introduced me. My name is Corey Harper, and today I'm going to talk to everyone about how we can transition from the transportation system that we have today to one that is more sustainable and smart. Okay. So, as some of you may know, I did my PhD and I did my master's at Carnegie Mellon. Most of my PhD research focused on the policy and infrastructure implications of connected automated vehicles on transportation systems. I did this research under the guidance of Dr. Chris Hendrickson and Dr. Constantine Smurres. They're two of my colleagues now, and I graduated in 2017. I went straight through, so I did my bachelor's, master's, and PhD. And part of me when I finished wanted to get some work experience. So that fall, after I graduated, I went ahead and did some consulting. Right, I started my career at Booz Allen Hamilton. And as Carly said, this was supporting clients from DoD, USDOT, national academies on infrastructure-related projects. And most of the work that I did helped the United States Department of Transportation with the integration of connected and automated vehicles. Right. While I was here, I thought this was some really good experience. I met some good people, and I worked here for about 2 years, but I didn't think that this was something that I wanted to do long term. So, in fall of 2019, I came back to Carnegie Mellon, and I started my postdoc here. Right. Most of my postdoc work looked at transportation network resilience and using some rainfall data. We'll touch on some of this later. And that fall, I went on the job market and was able to get a position at Carnegie Mellon in the Civil and Environmental Engineering Department, as well as the Heinz School of Public Policy. So I'll touch on some of the research that my lab looks to do and some of the research that my students are currently doing. So now I'm going to get into, my research vision, what I plan to do in my research, some of the things that I've done, what I plan to do in the future, right? So So my research uses systems modeling to help stakeholders make more informed decisions so that we have a smoother transition to more equitable and sustainable smart cities, right? So this graph captures what I think are some of the key components of a smart city. Smart economy and living refers to better access to job opportunities and reliable transportation options. Smart design refers to designing cities with people and pedestrian safety at the forefront. And smart mobility and environment refers to improving congestion and reducing energy use. Smart governance refers to those policies that shape the sustainability of the transportation sector. And today I'm going to walk you through how my research can help us get to that smart city. So what this graph shows is that all of the components of an urban system are connected, right? You have your blue components, which are your transportation system components, and you have your green components, which interact with the transportation system and affect it, and vice versa, right? And my research looks at the links between these components. For example, my research on automated freight looks at how platooning technologies could impact congestion on highways. And my research using rainfall data looks at how increasing frequency of heavy rainfall events could impact traffic flow. And, you know, what you see here on this list are, you know, people, climate, energy, food, right, in the green, right? People are at the top of this list because the goal of my research is to improve quality of life for people by looking at those emerging trends in transportation. So the first thing I'm going to do today is I'll go over an introduction about how robocars could change the way we envision our cities and communities. Then after that, I'll go over a study that we published on private robocars, where we developed an agent-based parking model. After that, I'll discuss some of the resilience work that I did during my postdoc. And finally, I'll talk about some of the other emerging areas in transportation that my students are currently exploring. So on this graph, you have your number of fatalities on the primary y-axis. On the x-axis, you have the years 1975 to about 2016. And on the secondary y-axis, you have your crash fatality rate, right? And, you know, so what you're seeing here is that from, let's say, about 1985 to about 2010, 2011, we're seeing a steady decline in the fatality rate. You know, this is good. This means that, you know, even though people might be traveling more, you know, we're seeing a lot less crashes on the roadway, a lot less deaths on the roadway, right? But, you know, around 2015, 2016, we started to see a spike in the number of traffic deaths and the traffic rates, right? And this is concerning because in 2015, there were about 32,000 crashes compared to about 35,000 crashes in 2016, which represents the biggest spike in traffic deaths in a one-year span in the past 50 years. In addition to this, pedestrian fatalities have also increased by 41% since 2008, which impacts the livability of many cities. So just to put this in some perspective, this is about 670 fatalities per week, which is greater than the capacity of a jumbo jet at its highest capacity configuration, which holds about 660 passengers. So in other words, even if there was a plane crash each week, this still wouldn't equal the total number of deaths that we experience on the roadways each year. So what do we do, right? You know, and like I said, you know, we're looking at those emerging trends in transportation. So connected and automated vehicles have the potential to address some of these issues and could very well be on our streets and highways within the upcoming decades. Automakers are already marketing cars with some automated features, such as lane keeping assist and adaptive cruise control. Some of you might have heard of these. You know, and a lot of cars today have automatic emergency braking. These are all automated features, and these companies are progressively working towards making more highly automated and self-driving cars. Car company Tesla is equipping every new Model S sedan and Model X SUV with the necessary technologies for full self-driving capabilities in exchange for about $7,000. Ride-sharing company Uber has deployed a fleet of self-driving taxis in Pittsburgh and in other cities around the country, and have even offered some customers the option of riding in these vehicles. And last but not least, the United States Department of Transportation has released their third policy document, providing guidance to automakers and other entities on the safe design, development, and deployment of some of these automated driving systems. So there's a lot going on. There's a lot of investments being made by private companies, and there's a lot of investments being made by the federal government as well. They're on board. So that's what I'm trying to get across to you all. So autonomous vehicles, they do three things, right? They sense, they plan, and they act. They sense the world around them by classifying stop signs, other vehicles, and pedestrians. They plan the next maneuver. For example, a stop sign is coming. What should I do? And the act, the physical connection of applying the brakes. All of these are similar to what a human would do, right, when driving. But the hope is that autonomous vehicles can do this better and much faster than we can without getting distracted. So the thing about automation is that we're not going to go from one of the vehicles that we have today to one that is fully driverless. There's likely going to be some progression. And a way to illustrate this is to use emojis, right? So these are the 6 levels of automation as defined by the Society of Automotive Engineers. You have your level 0, which is no automation, and level 5, which is full automation, right? And the emojis represent, so the robot emoji represents tasks that are done by the robocar, and the smiling emoji represents that task that will be done by the humans, right? So it's not until levels 4 and 5 that you'll begin to see people, sleeping in the back seat, watching a movie in the back seat, not really focus on the task of driving because the vehicle is doing all of those things, right? And, so those are your fully self-driving vehicles, right? And then you have your level 3 vehicles. This is kind of a gray area because the vehicle is responsible for driving and monitoring, but the human is supposed to be capable of intervening in case of an emergency, right? So, what's happening here is that the robocar is the main driver and the human is the backup driver, and we're not really good at being backup driver. We need to be engaged, otherwise we get bored, right? So this is kind of a gray area here. But what we're really good at is levels 1 and 2, right? Where the robocar is the backup driver and we're the main driver. And we've done a lot of work in this area in the past, looking at how some of these early level warning and partial automation systems could impact roadway safety. Now I'm not really going to touch on some of those projects today, but the research that we've done shows us that deploying these systems on all light duty vehicles could substantially reduce the number of crashes that occur each year, which is a big thing, and they could provide a lot of economic benefits, But what we are going to talk about today are some of our automated driving systems at levels 4 and 5, and we're going to talk about how they can impact the way that we plan our cities and communities. So one of the questions that we're interested in knowing as transportation engineers is, how are people going to use these vehicles, right? So are people going to be using these as micro shuttles, transporting people in and out of their urban cores? Or are people going to start living longer distances away from work as in-vehicle productivity increases, right? So for example, you see the picture on the bottom right, this person, they're sleeping on their way to work, they have their computer there, they have their work shirt there, so for the first 2 hours on the road, you could spend your time handling some meetings, checking some emails, then you get to work, you finish up your workday there, and on the way back, you sleep and you get back home. So this is, so these are some scenarios that we're really interested in exploring, and I'm sure COVID is going to have an impact on some of these. Maybe people might just work from home now instead of traveling 2 or 3 hours to work in their car. These are things that can impact the transportation network, and these are some questions that have a lot of uncertainty that we're really interested in as transportation engineers. Another thing that is of interest to us is, will people own or share these vehicles? There's a Tesla model where everyone owns their own automated vehicle, Or will there be some sort of shared AV pod that transports people around the city? There are a lot of transportation professionals that feel like, well, oh, of course these vehicles are going to be shared. But I think it's important to explore scenarios that don't lead to these outcomes. And if these aren't the outcomes that we don't want to encourage, then we have to be active in understanding this. So as robocars become more automated, we have to think about how the public realm prices parking. So in this picture, you have a street near Shady Shot, right? You have some apartments, you have some single family homes, and you have people parking on the street. So you have some mixed residential use here, right? And in this neighborhood, we price the public realm by requiring residents to pay for a parking sticker, and everyone else can only park there 2 hours at a time. So what happens if you park there is an enforcement officer is going to come by, they're going to check everyone's sticker. If you don't have a sticker, they're going to check your license plate. They're going to write that number down, and they'll come back 2 hours later. And if you're still parked there, they'll give you a ticket. So right now we're pricing the public realm in many urban areas by requiring residents to pay for a parking permit. So, you know, like I said, this street is in Shady Side. So if this street didn't have one of these residential parking signs, one could, in theory, now I'm not encouraging anybody to do this, but you know, you could park there and walk 15 minutes to campus if you wanted to avoid parking charges, right? So what happens when you have a robocar that can decouple the proximity value of where it drops you off and where you have to park? So let's say you're driving to Carnegie Mellon and you have to decide where to park. Some of you might be willing to, you know, so there's a CMU garage, right? It might cost $8, $9, $10, $11, $12 to park there for the course of the day. You know, some of you may do that. It's on campus, it's close to one of your classes, you're late, you know, so you want to park in the closest available parking spot, right? So you pay the $12, right? Some might come to campus and they might want to search for the free parking spot closest to wherever their destination is, right? But most likely you're going to have to walk back to campus, right? You might have to walk 15 minutes. You know, it's in Pittsburgh, it's July, it's sunny out. So, you know, some of you may not mind doing this. But there are some people that will, you know, but nonetheless, there is some value that we're all willing to pay to be close to our parking destination. So what we did was we created a agent-based model to see what would happen to parking in downtown urban cores, paid parking in downtown urban cores, if the robocar could drop me off at my destination, search for cheaper parking, and come back to pick me up when I was ready. Before the study was done, there were several researchers that looked at how shared AVs could impact parking. This paper took a different approach by focusing on privately owned vehicles. So here's the city of Seattle. This is where we conducted our case study. So in the green, you have your unrestricted parking zones, where anyone can park free throughout the course of the day without any restrictions. And in the red, you have your parking lots and garages in the downtown urban core. And what we did here was we modeled the unrestricted parking in the city of Seattle by identifying those areas that had abundant amounts of unrestricted parking, right? So what we did here was we modeled about 67,000 total unrestricted parking spaces. And what we did was we assumed about half of these would be available throughout the day. So there would be about 33,000 available parking spots for these AVs to, you know, have a place to go to. So yeah. So what's happening in this model are each AV is an agent, and they're searching for cheaper parking, right? So here are your two options, right? You can either park downtown, or you can go to one of these unrestricted parking zones. So the objective of each AV is to minimize the total cost to the user, right? And this is the total cost to the user is the summation of your round trip cost of driving and your daily parking, right? And what your cost of driving takes into account is It takes into account fuel, it takes into account tires, it takes into account depreciation, and it also takes into account the distance you drove from point A to point B. And you also have your daily parking costs, right? So in your downtown urban area where you see all of the parking lots and garages, there's going to be a fee for you to park at one of these parking lots, right? But outside of the downtown area in one of those free unrestricted parking zones, there's going to be no fee, right? So, but the thing is, you're going to have to travel far to go to one of these spots. So what we're trying to see is, from an economic standpoint, what's more feasible for you to travel, 12, 14 miles back and forth to avoid parking charges, or is it more feasible for you to go to the closest parking lot downtown that's inexpensive and park there instead? So that was the objective of the AVs in our model, right? And they're all subject to parking availability, right? So each one of these zones has a set available number of parking spots. And, once the parking at one of these zones fills up, the AV can no longer choose to go there. So that was one of the constraints on our model. And for each parking spot selected by the AVs, there are energy implications. The increase in energy use is the product of the emissions factor. The emissions factor is the greenhouse gases emitted from each vehicle traveling to one of their parking spots. And then you have the fuel economy. This is the average average fuel economy of the passenger fleet in Seattle, right? And then you have the additional empty vehicle miles traveled generated by traveling for cheaper parking. And this is how we estimated our energy use and some of the implications from these vehicles going to some of these more distant, cheaper parking locations. So what we did first was we put a single AV in downtown Seattle and have it rank its parking choices just to see how the AV chooses parking, and then later on I'll show you what happens once we increase this penetration rate, right? So we did this to demonstrate parking decisions by AVs and visually demonstrate this, right? So what the AV does is it ranks all of its parking choices in terms of economic cost. And due to the low cost of driving, the AV is going to choose the free parking spot closest to its starting point, right? And it's going to circle through all these, and then it's going to choose this. If no parking is available here, it's going to go to the second spot with the lowest cost, and the third spot with the lowest cost, and so on and so forth until an available parking spot is found. So what happens when we start to increase the market penetration rate of AVs downtown, right? We saw what happens when you have one AV, nobody's competing for parking as yet. It can pretty much get all of the zones closer to it. So its first, second, and third parking spot are, the free parking zones closest. But what happens when these spots fill up and they have to travel farther distances? What decisions does it make, right? So currently in the downtown area, you see a lot of green, right? Red represents there's nobody in these areas. You see no red right now, right? You see a lot of green downtown, which means that a lot of the parking lots and garages that are paid have really high occupancy rates, right? A lot of them have anywhere between 75 and 100% occupancy. So people are paying to be there, and the owners of these infrastructure systems, they're really happy, right? And in your unrestricted parking zones, you see a lot of yellow, right? So everyone is assumed to be about 50% full now. And what we're going to do is we're going to increase this number, and we're going to see what happens as we start to introduce more AVs that can park away from your destination. So at the 25 AV penetration rate, right, you start to see that AVs begin to leave downtown, and they start to fill up the free parking close to the downtown area, right? And what you're seeing downtown is no more dark green, right? This means that a lot of AVs have left, and what you're seeing on the in the free parking zones closest to downtown, you're seeing a lot of dark green, right? So AVs are starting to leave the downtown area, and they're starting to fill up the unrestricted parking zones closest to the urban core. Now we have 50% penetration rate of AVs, right? You no longer see any green, so, at this point in time, a lot of parking lot garages, owners and operators, they're going to start to suffer, right? And you might start to see some of the paid parking lots downtown become unprofitable, right? Because people are leaving, right? Now, we didn't model these parking lots and garages as agents, but most likely what would happen is if people are leaving the downtown area in search of cheap parking, the parking lots and garages downtown are going to adjust their prices to compete with this cheaper parking, right? But what you're saying right now is the lots downtown have really low occupancy rates, and AVs have filled up the unrestricted parking zones close to the downtown area, and they're starting to travel farther distances for a cheaper parking. And now at 100% AV penetration rate, every single AV leaves the downtown area. There are no more cars parked downtown, and there's no longer any economic incentive to own and operate a parking lot. And what this goes to show is that there's enough free parking close to downtown that AVs can choose to park somewhere else. Now, on the previous slide, I showed you that all of the AVs are going to leave the downtown area because it's cheaper to park in one of these unrestricted parking zones, right? And a big part of this is because the operational cost of driving is really low, right? So this is the operational cost of driving. So like I said, it takes into account fuel, depreciation, tires, maintenance, and it doesn't take into account insurance and things like that, because whether you drove to these parking spots or not, you have to pay some of those costs, right? But this parking cost is low. The lowest cost to park in the downtown area is about $7. So, the round trip break even distance is about 28 miles, right? So up until that point, if your free parking spot is within 28 miles, the AV is going to choose to park in one of these unrestricted parking zones, right? And I'll touch on some policies that maybe can, we can deal with this later, because if we're all coming outside of our homes and there's an AV park there, we're going to start to get mad. And, like I said, some of those signs that you saw earlier where, you have 2 hours of parking and stuff, some of these might end up popping up in some of these areas if AVs are taking everyone's parking spot, right? So, one of the things that we wanted to see was, would VMT, would energy use, would all these things increase by a substantial amount if everyone's leaving the downtown urban core? And, the data set that we looked at, it's a sample of the vehicles parked in downtown Seattle, right? It just looks at the parking lots and garages that have daily fees, right? So we didn't see big increases in some of these numbers. And that's just because there's so much more cars traveling in and out of Seattle than there are cars parked downtown. So you'll see some increases, and you might see big impacts on certain corridors. But overall, we don't see substantial increases from AVs leaving the downtown urban corridor and going to some of these more distant parking locations. So parking is a big business in Seattle, right? They generate about $170 million in annual revenue from people parking downtown, right? So a lot of money could be lost if cars move away from the downtown area, right? But this does mean that land will be freed up for other uses, right? So bike lanes, parks, houses, libraries, and shops, you could all see these things in the future. And like I said, right, so each AVs are traveling about 8 miles per day. This is about a 2.5% increase in VMT and energy use, but there's going to be specific corridors that bear the most impacts, right? So a 2.5% increase in vehicle miles traveled, that could be a big increase in congestion on some corridors, especially if a lot of cars are already traveling here during peak hours, right? So, and as a policymaker, some things that you might think of doing are, creating a tax for people that want to leave the downtown area in search of cheaper parking. You incentivize them to stay downtown instead of, traveling and avoiding some of these parking costs. And what if AVs were shared, right? What if there were EVs? What if they could boost transit? These are all questions that, we'd like to explore in the future. And I'll touch on some of that later in our future study. So now I'm going to move into some of the current work that I'm doing on hazardous modeling, right? And, you know, this is important because of climate change, right? We're starting to see an increased frequency of heavy rainfall events in our transportation network, which could lead to increased flooding on roadways. And what goes on a lot of times when there is heavy rainfall is that roads close and roads flood, right? But we're not able to see a lot of these things until we get home. You know, we're eating dinner, we turn on the news, and then we get to see, you know, which roadways flood, right? But by then it's too late. If we don't know this in real time, people could drown, and there could be gridlock in the transportation network because when there's flooding or when there's accumulation of water, people have to slow down. So what we're trying to do is predict 30 minutes ahead what travel speed will look like in the transportation network. And this is so that infrastructure owners and operators can make more informed decisions on when to divert traffic and when to close down roadways. In the past, hydrologists have tried to do some of this work, but what we do is take a data-driven approach to look at this issue from a different perspective. So this figure shows the overall procedure flow for the study, right? First, we define our study area and gather the data that will need to be incorporated into our machine learning model. Some of the data that we incorporate into our initial feature set let us know the state of the transportation network. So we incorporate data for travel speed, incidents, weather, and a few other features I'll touch on later. And for this study, we focus on Washington Boulevard as our target segment due to the heavy rainfall this roadway experiences. If you're from Pittsburgh, you know about Washington Boulevard, you know, they have gates there, and this roadway tends to flood a lot. So we thought this would be a good case study for this model that we built. After we do some data collection, then we model our data by wind direction, right? And I'll touch on why we do this in some of the following slides. And we conduct a correlation analysis to identify the relationship among the different features in our feature set. And then we use Lasso to select a subset of features that is going to be incorporated into our final machine learning model. And finally, we evaluate the performance of several different machine learning models on our data. And the final output of these steps are travel time prediction values 30 minutes from now. Now, this is our study area, right? So like I said, our target segment in green is Washington Boulevard. We have some alternative routes in dark blue, and we have the main highway in Pittsburgh, I-376 in light blue. And we have some other main arterials in the area in dark red, right? Now, one of the unique components of this study is the rainfall data. So we have a lot of rainfall data. We have our gauge adjusted radar rainfall pixels. These are those square blocks that you see. These provide an estimate of rainfall for each 1 kilometer squared area across Allegheny County for every 15-minute interval. And then we have 33 rain gauges scattered around the city, right, providing observed rainfall reading. And what most studies do is they use one rainfall data point, right? So a single rainfall data point that's supposed to tell you what rainfall looks like in that region, right? So most studies use one rainfall data point. And so let's say I was using the classical method of a single citywide rain gauge. Where you see this square at is near the airport, right? The National Weather Service has a rain gauge near the airport. So if I was just using, you know, National Weather Service data to inform my model, I would have one data point here near the airport used to inform my model. So I'd be missing some information that I'm capturing with some of this data, right? And what we're hoping is that by including this rainfall data, we can develop a more accurate prediction model. So, you know, and the point of this is that rainfall can vary greatly over a region, right? So where you saw that red square at is in the upper left corner of Allegheny County, right, where a lot of the red is, right? Now, what if my target segment was down, you know, to the bottom right of Allegheny County, where a lot of the blue is, right? So my rain gauge is telling me that there's heavy rainfall. That's what the red indicates, and the blue indicates that, the total rainfall is a lot lower, right? So, the point is that you're missing some information that you're not capturing, and that we're hoping by capturing this, we can have a better sense of what rainfall looks like in the network and build a better prediction model. So the one thing we did was we grouped rainfall data by wind direction, right? And we focused on the southwest wind direction, and that's what I'll walk you through today, because the prevailing winds in Pittsburgh are from the southwest region. So that's why we focus on this quadrant for the study. And the reason why we did this is because there are a lot of rainfall features, thousands of rainfall features. And it could be really hard to discern why the machine learning model is picking one over the other. Also, rain clouds travel with wind, which means that these rainfall features will likely be the best predictors of rainfall in the transportation network 30 minutes from now. And what this graph shows is a subset of the speed and rainfall features, which were all selected by LASSO. And we do this to improve prediction performance and reduce overfit. Most of the rain gauges and pixels selected for this model are relatively far away, indicating that the rainfall features far away provide the most useful information on the state of rainfall in the network 30 minutes from now. And one important aspect of our paper, like I was mentioning before, is that we wanted to compare the performance of our model using high resolution rainfall features with the classical method of using a single citywide rain gauge. And what our results show is that using higher resolution features does improve overall performance. But the magnitude of these improvements in those weather conditions where the model performance improves is likely to vary by the roadway segment. And here for Washington Boulevard, we see the most substantial improvements in model performance during moderate and heavy rainfall events, right? And, so what we're seeing is that using the classical method of a single rain gauge, we get about 18.9% make during heavy rainfall events, whereas if we use high resolution rainfall features, we get around 18%, right? And that's about a 4% improvement in model performance overall. Now, I know some of you might be saying to yourself, well, Corey, those model performance, you did all that work to get, from 18.9 to 18%. It's only raining, it's not raining every day. These heavy rainfall events are rare, but the thing about traffic safety is that even small improvements in traffic safety provide huge benefits, right? So for example, in 2018, there were 900,000 crashes that occurred that year in inclement weather, right? If we could even eliminate a small percentage of these crashes, let's say 0.1%, then you could see benefits of over $160 million annually, right? And if you get to even 1% improvement in road conditions during inclement weather events, you could start to see 1.6, and even if you got to the 4%, you could see some really big benefits. So you don't need huge improvements in traffic safety to provide huge benefits. So here are some of our conclusions. We see that, many of the rainfall segments are far away from our target segment, and that means that these segments, are providing the model with information. And although it's imperfect, these segments are providing the model with useful information to predict travel speed on Washington Boulevard 30 minutes ahead. The incorporation of high resolution rainfall features also offers overall improvements in model performance when compared to only using a single citywide rain gauge. But the magnitude of these improvements in those weather conditions where the model performance improves is going to vary by roadway segment. And high resolution features could have much higher correlations with future rainfall on Washington Boulevard, leading to substantially better predictions during certain rainfall events. So, I talked to you about some of the research that I did during my PhD and some of my postdoc research. Now I'm going to talk about some of the research that my students are currently doing. And what you see here is a chart that outlines the 4 key areas that are going to guide my research. And, you know, for the next few slides, I'll walk you through what I'm currently up to right now. So one thing I like to do is reimagine the way people travel in today's urban areas, right? Currently, most cars are done by, most trips, short vehicle trips, 0 to 3 miles are still done by car, right? And the thing about this is these could be replaced by micromobility options, right? So micromobility, you know, these are your bikes, your scooters, your shared bikes, right? And, you know, so the thing is people are doing these by cars, but, you know, people could do these by other options, right? So for example, in Pittsburgh, about 50% of short vehicle trips are done by cars, right? And a lot of times these are done single occupancy travel, meaning that a person travels in the car by themselves. You know, they go to the gym, they go to the convenience store, and then they come back home, right? And, you know, the thing is that these have impacts on congestion, and a big motivation for this project is the fact that the transportation sector is the biggest emitter of greenhouse gas emissions in the United States, right? And these short vehicle trips contribute a lot to that, right? So how could we, you know, and a lot of state and local agencies are looking to see how could we begin to reduce this travel, right? So one thing that could get people out of their cars are these micromobility options, right? And what you see in this picture is a shared vehicle service, Healthy Ride in Pittsburgh. It's right outside of Carnegie Mellon, and it's right on Few Street. And you know, I see Joy, so I'm gonna explain this one project, then I'm gonna wrap it up, all right? Because my 40 minutes is ending pretty soon. You know, I've received some seed funding from Traffic 21, and one thing we're looking at is, you know, so in the past slide you saw 50% of short car trips can be replaced, right? So what we're trying to do is develop an upper bound, right? This doesn't take into account limitations on replacing some of these short trips, right? So you could have weather. You know, nobody wants to ride their bike when it's raining, you know, or when it's snowing out. And you also have physical limitations of some riders, right? So some people have disabilities, you know, or they're elderly, you know, so, and these people are not likely to replace their short car trip with micromobility. So, you know, the first thing we want to do is, you know, what's the upper bound? And then once we figure out what the upper bound is, we want to see what happens when we start to replace short car trips with micromobility options and what impact that has on traffic congestion, energy use in the transportation sector, right? So I'm going to wrap it up now. If there's nothing else you leave with today, it's that I envision a future transportation system that's strong and robust to extreme weather events, promotes public safety, and promotes sustainability. And I think that the research I have on hazardous modeling, micromobility, and automation can help us get there. I hope everyone enjoyed this presentation. Are there any questions?
I have lots of questions for you, Corey.
Okay.
The first is, has the trend of rising fatality rates continued since 2016?
Since 2016, I think at some point, I think it started to go down, the overall fatality rates, but what we started to see recently was an increase in the number of pedestrian fatalities in many urban areas. So, so they are going down overall, but there's still some concern because, you know, we want to create sustainable smart cities, right? And if you're going out, you're walking, you're biking, and you're at risk of getting into a crash because of that, then it's not a good thing. So that's a big concern right now for a lot of transportation engineers.
Okay. What implications does the agent-based model have for public transportation?
Public transportation. So let's see. So this study really looked at probably on vehicles, right? Now, you know, I don't know if it'll have too much impacts on public transportation. You know, just because the people that are using these parking lots and garages right now to go to and from work, you know, they aren't transit riders, you know, so they're used to using a privately owned vehicle for their day-to-day travel, right? Now, if we want to get them to use public transit, I don't know how far away they live. You know, we could provide some incentives, you know, to get them out of their vehicle and into more, you know, public transportation systems. But you know, the model right now looks at privately owned vehicles and doesn't really look at transit-dependent populations. So maybe that's some future work that we can take a look at in the future and incorporate some of their utilities and some of their preferences for mode choice for transit riders into our model.
Okay. How challenging is it for students as well as professors coming from various backgrounds to work in these areas?
So, I mean, let's see. So when I first came to Carnegie Mellon, I didn't even know I'd be doing transportation engineering, right? I thought I'd be a structural engineer doing some structural health monitoring, you know, but you know, when I got my offer to come to Carnegie Mellon, I saw I had an opportunity to work with Chris, Traffic 21, and I got really excited, right? So, I mean, I guess the first thing is, you know, having an open mind, and if this is something you're interested in, you're gonna have to find somebody who's doing this work and has some funding for you to do so. You know, I found this work really interesting, you know, and it, you know, and I can explore some topics that are really interesting to people. So, you know, I think, you know, let's see. So when I was doing my PhD, you know, one opportunity that I had that I thought was really unique was I was able to do an internship at the National Highway Traffic Safety Administration. I was a vehicle safety researcher there, and you know, that's something that, you know, I encourage a lot of people to do. It's the summer transportation internship for diverse groups, and you know, that helped me land my first job, and I thought that was some really good experience for me to see things from, you know, from more of a regulatory perspective. You know, I think there are a lot of transportation opportunities out there, and you know, you have to, you know, you can explore those.
Okay. Were you able to use Dr. Chen's LSTM network to estimate parking availability, and what was the best way to estimate unstructured parking without parking payment data?
So let's see. So it sounds like they're asking about the unrestricted parking zones that we modeled. So Seattle has a lot of data on their on the state of their transportation system, and they have some pretty robust data on what their parking looks like now. So I think what we did was we looked at a data set that it pretty much outlines every single lane mile in the city of Seattle, and you know, reports back whether or not, you know, you have to pay to park here, you have to have a parking pass or sticker to park here, or whether it was unrestricted parking. And what we just did was we said, okay, well, what are the areas that have abundance amounts of unrestricted parking available? And we just modeled those areas and, you know, estimated the number of parking spots there, and, you know, assumed a certain number of these would be available during the day, and then the AVs were able to travel there.
The optimization object, or the cost function, is with respect to the price that has to be paid for parking. However, other factors like the fuel consumption and traffic also play a role in it. How do you tackle this problem?
Joy, could you repeat that again?
Sure. The optimization object, or the cost function, is with respect to the price that has to be paid for parking. However, other factors like the fuel consumption and traffic also play a role in it. How do you tackle that problem?
Right. So fuel consumption is incorporated into our model, right? Traffic congestion isn't incorporated into our model, right? And so the thing about it is, this is an economic decision-making model, right? And you know, so if you're in congestion, you know, there's going to be some wasted time, there's going to be some extra wasted fuel that occurs, you know, and the best way to model this is to adjust that operational cost of driving. So our base case assumes about 25 cents per mile. This assumes that the person just travels back and forth with no issues. But if you encounter congestion or anything else along the way, then we did a sensitivity analysis to see what would happen and to see at what price point AVs would start to make different decisions, right? So if there's some congestion, your operational cost goes up. If there's a tax, your cost goes up. And we tried to see what would happen if we would vary this cost. We started at, let's say 5 cents, 25 cents in our base case, and we went up to well over $1. And it pretty much turns out that, especially, at the beginning where, you're able to get some of your first, second, and third parking choices. Most of these AVs aren't going to make different decisions. It's not really until they have to travel really long distances to get to cheaper parking that they begin to make different decisions if the price of driving increases.
Okay. Did you consider the option of the vehicle driving the entire day? While it might be a great option, are there any situations that it has economic benefits?
So let's say I can think of one. It has economic benefits. So, let's say I own a Tesla. Instead of parking my car during the day in a garage, a paid lot downtown, I could have it pick people up and drop people off while I'm at working. So, that's one economic benefit I can see is, you have your own shared AV service that can operate while your car is not in use.
That's all the questions I
That's all
have.
the questions. Okay.
And this is Lisa Kay from Traffic 21 and Mobility 21. And I would like to thank Dr. Harper for being part of our session today and sharing information about his research and the different projects that he did as a student, what he's doing now, and what he's working on with his students today. I'd like to thank everybody else for joining us today, all the participants. The Smart Mobility Connection Series is sponsored by Traffic 21 and the Mobility 21 University Transportation Center as an opportunity for faculty to showcase their current transportation projects. It's also an opportunity for students, fellow faculty, deployment partners, and the broader community to engage and network with researchers, highlighting opportunities for involvement and fostering future interdisciplinary collaboration. As we mentioned earlier, today's presentation will be posted on the Mobility 21 What's Happening page, along with a link to the video of the session. This afternoon, you will be receiving an email asking you to take a short survey about today's seminar. Please take a few minutes to provide your feedback. And for students who are interested in engaging in transportation topics, please remember the Carnegie Mellon University Transportation Club is a great way to plug into transportation topics and meet up with your fellow transportation nerds. Our next Smart Mobility Connection seminar will be on Friday, October 9th with John Piha, and he will be speaking on spectrum policies for connected vehicles. Please watch your email for an invitation early next week. Again, Dr. Harper, thank you. And thanks to everyone for attending today. And feel free to contact us with any questions. Thank you.